Welcome viewers. We already know that current carrying conductor placed in a magnetic field experiences a magnetic force. In today's program, we will extend our learning and understand what will happen if a rectangular current carrying loop is placed in a uniform magnetic field. Also, we will understand how this concept is employed in the galvanometer. And today we will take the concept of magnetic field to the atomic level and understand the atomic magnetic moment. Let's begin with the simple case. Here in the given diagram, ABCD loop is placed in a magnetic field, and this plane is such that it lies in the plane of magnetic field, uniform magnetic field. So first of all, what we have to do is we have to find out the force on BC and AD. Now this BC and AD, the line elements of these two, the current elements of these two arms is in the direction of magnetic field. So it will not experience a force at all. But if I talk about AB and CD, the current element of AB is perpendicular to the direction of magnetic field. And same with the case of CD. The current element of CD is perpendicular to the magnetic field. Now to find out the direction of force, we will use right hand rule. So what we will do is we will align our fingers in the direction of F and thumb in the direction of current. So the perpendicular of this palm will give the direction of force which is into the plane. But in case of CD, the direction of B is this, but the current is in downward direction. So the perpendicular to the palm will give me the force. Now let's talk about the magnitude of the forces. In case of length AB, the F1 is given by current multiplied by length of the conductor and the magnetic field. Here the length is B. Similarly, in case of F2, it is given by I small b multiplied by capital B, because again here the length is small b. As we have already discussed that both the forces have opposite directions, but here we can also see that they have same magnitude. Then what will be the net force on the loop? Of course, it is 0. Let us view the loop from the AD end. There is a torque on the loop due to the couple of forces F1 and F2. It means it shows the torque in the anti-clockwise direction. Let's talk about the torque. We will calculate the torque by adding the moment of forces. Here the moment of forces will be given by F1 A by 2 plus F2 A by 2, where F1 and F2 is I small b multiplied by capital B. On solving it, we will get I multiplied by small ab multiplied by b. Here AB is nothing but the area of the rectangle. So now we have the expression of the torque experienced by the rectangular loop placed such that the uniform magnetic field B is in the plane of the loop and the normal of the coil makes an angle 90° with magnetic field. Further, we will take the case where the plane of the loop is not along the magnetic field, rather it makes an angle with it. Now here in the diagram, we can see that the plane of the loop is making angle theta with the magnetic field. So here on the arms BC and AD, the forces are there and they are equal and opposite. But because they are on the same axis, it means they are the collinear forces, so there is no torque. Let's find out the forces on arms AB and CD. Look at the diagram. Here also F1 and F2 are equal and opposite, same as the previous case. Since these forces are not collinear, so it forms a couple and produces torque. But in this case, perpendicular distance between the forces of the couple has decreased, so as the torque will decrease. Now, we will calculate the magnitude of the torque on the loop, which is again is the sum of the moment of forces, which is F1 A by 2 sine theta plus F2 A by 2 sine theta. From here on solving it and substituting the value of F1 and F2, we will get I multiplied by A into B, which is nothing but the area of the rectangular loop B sine theta. So the torque is IAB sine theta. Now, can we express the torque in vector form? Before moving ahead, look at this diagram again. We can see the letter M pointing normal to the plane of the loop. This M is nothing but the magnetic moment. Let us define the magnetic moment first. We define the magnetic moment as M equals to IA. Since the magnetic moment is the product of I and A, so the dimension of the magnetic moment is given by A L square, and the SI unit of the magnetic moment is given by ampere meter square. Now coming to the torque on the loop. As we know that torque is IAB sine theta and we know that IA is M, so torque is given by the cross product of magnetic moment and the magnetic field. Do we have seen this kind of expression before? Actually, this is analogous to the electrostatic case where torque on an electric dipole placed in an electric field is given by torque equals to the cross product of electric dipole moment and electric field. Let's understand more about torque. What happens to the torque on the loop when M is either parallel or anti-parallel to the magnetic field B? At theta equals to 0 or 180 degree, the torque becomes 0 according to the formula IAB sine theta. Now when M and B are parallel, it means theta is equals to 0 degree. The equilibrium is called the stable equilibrium. And any small rotation of the coil produces a torque which brings it back to its original position. When they are anti-parallel, anti-parallel means when it is making an angle 180 degree. This time, this equilibrium is called unstable equilibrium, as any rotation produces a torque which increases with the amount of rotation. The presence of this torque is also the reason why small magnet or any magnetic dipole always aligns itself with the external magnetic field. Moving forward, we shall consider the elementary magnetic element, that is the current loop. We will try to establish the similarity between magnetic field at large distances due to the current in a circular current loop and the electric field of an electric dipole. We already know that the magnetic field on the axis of a circular loop is given by B is equals to mu naught I r square divided by 2 x square plus r square raised to the power 3 by 2. If x is very large as compared to the radius of the loop, then this r can be neglected and we can have the magnetic field as mu naught I r square divided by 2x square. On multiplying and dividing the previous equation by pi, I can replace pi r square by a, which is the area of the loop. Since m is equals to Ia, so I can replace Ia with the magnetic moment and I can have B equals to mu naught m 2 pi x cube, and on multiplying and dividing it by 2, I will have mu naught by 4 pi multiplied by 2m divided by x cube. Let's recall the expression obtained for the electric field of a dipole. The similarity may be seen if we substitute mu naught by 1 by epsilon naught, m by replacing it by Pe, B as E, then I can have E is equals to 2 Pe divided by 4 pi epsilon naught x cube, which is nothing but the field for an electric dipole at a point on its axis. Let's carry this analogy further. The electric field on the perpendicular bisector of the dipole is given by Pe divided by 4 pi epsilon naught x cube. If I write P as m and mu naught as 1 by epsilon naught, I will have the expression of B as mu naught by 4 pi m by x cube. Again I am considering that x is very large as compared to the radius of the loop. Now the results obtained can be shown to apply to any planar loop. And now we all know that a planar current loop is equivalent to a magnetic dipole of dipole moment m equals to Ia. which is analog of electric dipole moment P. We were establishing analogy between electric field and magnetic field in terms of electric and magnetic dipoles, but there is a fundamental difference. Can you think of it? An electric dipole is built up of two elementary units, that is charges. It means a single charge can exist. Yes, electric monopoles can exist, but in magnetism, a magnetic dipole or a current loop is the most elementary element. The equivalent of electric charges, that is magnetic monopoles, is not known to exist. Next, we will calculate the magnetic dipole moment of one of the elementary particles, that is a revolving electron. This is the picture of Niels Bohr, a Danish physicist. In 1911, he proposed a model of hydrogen atom, which is known as Bohr model of the hydrogen atom. It was a stepping stone to a new kind of mechanics, namely quantum mechanics. According to the Bohr model, the electron revolves around a positively charged nucleus much as planet revolves around the sun. However, the force in the former case is electrostatic, that is Coulomb force, while it is gravitational in the case of planet revolving around the sun. Let's see the Bohr picture of the electron. Here, electron is revolving in the anti-clockwise direction around a heavy nucleus of charge plus Ze. Conventionally, the current produced by this electron will be in clockwise direction. On using right hand rule, we will find that the direction of area vector is into the plane, which is same as the direction of magnetic moment. As we have discussed that the electron of charge E, which is minus 1.6 into 10 raised to the power minus 19 coulombs, revolve around the nucleus of charge plus Ze. This constitutes a current I, where I is given by E divided by T, which is the time period to complete one revolution, which is given by 2 pi r divided by velocity. Now here mu L is representing the magnetic moment due to a revolving electron, which is the product of current and area. Here we can have the current from the above two expression, and we will have mu L as EVR divided by 2. On multiplying the right hand side of the equation and dividing it by ME, we will have MVR in the numerator, which is nothing but the orbital angular momentum, that is L. So, in vector form, I can write mu L as mu L equals to minus E by 2 ME into L. The direction of orbital angular momentum is given by right hand rule with respect to the velocity of the electron. So, in this case, that will be out of the phase. So, this negative sign indicates the angular momentum of the electron is opposite to the direction of magnetic moment. But yes, if instead of electron we have charge plus q, the angular momentum and magnetic moment would be in the same direction. Next, we will discuss the gyromagnetic ratio. It is the ratio of the magnetic moment of the revolving electron to the orbital angular momentum, which is given by this equation. If I take this L to the left hand side, we will have this ratio equals to minus E divided by 2 ME. On substituting the magnitudes of E and ME, we will have the value as 8.8 into 10 raised to the power 10 coulomb per kg. This value has been verified by experiments. It means even at an atomic level, there is a magnetic moment. It confirms Ampere's Bohr hypothesis of atomic magnetic moments. According to Ampere, this would help one to explain the magnetic properties of materials. Can one assign a value to this atomic dipole moment? The answer is yes. And with this, we are going to define Bohr magneton. Okay, let us consider the Bohr model. Bohr hypothesized that the angular momentum assumes a discrete set of values, and it is given by L equals to nh by 2 pi, where n is the natural number 1, 2, 3 and so on, and h is the constant which is called Planck's constant. Now, this condition of discreteness is called the Bohr quantization condition. We wish to calculate the elementary dipole moment. For that, we will substitute the expression of L in the expression of magnetic moment for a revolving electron, and after that we will get E divided by 4 pi me multiplied by h. Here we have taken n is equals to 1, that is why we are writing here mu L minimum. And on substituting the magnitudes of E, that is 1.6 into 10 raised to the power minus 19, H 6.63 into 10 raised to the power minus 34, 4 pi, and then Me, which is 9.11 into 10 raised to the power minus 31. And here on calculating this expression, we will have mu L minimum as 9.27 multiplied by 10 raised to the power minus 24 ampere meter square. This value is called the Bohr magneton. So, we got to know that any charge in the uniform circular motion would have an associated magnetic moment. This dipole moment is labeled as orbital magnetic moment. Do you know that other than orbital magnetic moment, there is another magnetic moment? Yes. Besides the orbital magnetic moment, the electron has an intrinsic magnetic moment, which has the same value as of mu L minimum, and it is called spin magnetic moment. But remember that it is not as the electron is spinning. Nevertheless, it does possess this intrinsic magnetic moment, and the microscopic roots of the magnetism in iron and other materials can be traced back to this intrinsic spin magnetic moment. So, with this we discussed magnetic moment associated with a current carrying coil and with elementary particle like electron. Moving on, try to think about how are we able to measure the voltage drop across the conductor and electric current in a circuit. Let's begin with understanding of the working of important instrument called moving coil galvanometer. This is the diagram of moving coil galvanometer, which consists of the coil of many turns. It is free to rotate about a fixed axis in the uniform radial magnetic field. Here we can see the soft iron core, which has the dual role here. First, it is providing a radial magnetic field to the coil. Second is, it is increasing the strength of the magnetic field. As we have discussed that when a current flows through a coil placed in a magnetic field, it experiences torque. And here the spring SP provides a counter torque that balances the magnetic torque, resulting in steady angular deflection. Let us understand this thing mathematically. Here the restoring force is equated with magnetic torque. Restoring force is K phi, where K is the torsional constant and phi is the angular deflection, where I and AB is the magnetic torque. Now we can find out the phi from here, which is NAB divided by K multiplied by I, and phi divided by A is given by NABK. The quantity on the right hand side is a constant for a given galvanometer. The galvanometer can be used in a number of ways. First is, it can be used as a detector to check if a current is flowing in the circuit or not. Second, it is used in various electrical setups like Wheatstone bridge arrangement. In that case, the neutral point or the null point of the pointer, that is where is no current is flowing through the galvanometer, is in the middle of the scale. Depending on the direction of the current, the pointer's deflection is either to the right or to the left. So, as we have discussed that it can detect the presence of current, can we use it to measure the current like ammeter? No, we can't. There are two reasons. One is, galvanometer is very sensitive device and it gives a full scale deflection for a current of order microampere. Second reason is, for measuring currents, the galvanometer has to be connected in series, and as it has large resistance, this will change the value of current in the circuit. means it will not give the actual value of the current in the circuit. Then what can be done? To overcome these difficulties, we will connect a small resistance called shunt resistance in parallel to this arrangement. In that case, most of the current passes through the shunt and a very small portion of current passes through the instrument. It prevents the damage of the galvanometer. So here, as both are connected in parallel, so we can give the effective resistance with this expression. So if Rg is very large as compared to Rs, it means Rs has a very small value in relation to the resistance of the rest of the circuit. So the effect of introducing the instrument to measure the ammeter is also very small and negligible. This gives the accurate value of the current in the circuit. Ammeter is calibrated to measure current in a certain range by calculating the value of the shunt resistance. Now let us talk about the current sensitivity of the galvanometer, and it is defined as the deflection per unit current, which can be found out by using this expression. By taking I on the left hand side, we have deflection per unit current as NAB divided by K. Now we can increase the sensitivity by increasing the number of turns of the coil, then by increasing the area of cross section, then by increasing the strength of the magnetic field of the permanent magnets, and by decreasing the torsional constant, and it is all done at the manufacturing level. In the similar way, we will understand how we can use the galvanometer as voltmeter. Voltmeter is also connected in parallel to the component of the circuit, whose voltage needs to be measured. So it must draw a very small current, otherwise the voltage measurement will disturb the original setup by an amount which is very large. Usually, we wish to keep the disturbance due to the measuring device below 1%. Here is the schematic diagram to show how galvanometer is converted into voltmeter. To ensure this, a large resistance R is connected in series with the galvanometer. Note that the resistance of the voltmeter is the sum of resistance of the galvanometer and the large resistance of the resistor connected in series with the galvanometer. It results in the large resistance of the voltmeter. The scale of the voltmeter is calibrated to read off the voltage value with ease. Now let us talk about the voltage sensitivity. It is given by deflection per unit voltage. So we will find it by dividing both the sides of this equation by V, and from here we can see that I by V can be replaced by R. So the deflection per unit voltage is given by this expression. Now the question is, if we increase the current sensitivity, will it also increase the voltage sensitivity? Let us try to figure out the answer of this question. Here we know the expression for the current sensitivity. If I double the number of turns, the current sensitivity will also get doubled. Now in case of voltage sensitivity, this voltage sensitivity depends on N as well as R. On doubling the number of turns, it also doubles the resistance, which cancel out the overall impact, and there is no change in the current sensitivity. Now we can say that the modification needed for conversion of galvanometer to an ammeter will be different from what is needed for converting it into voltmeter. So with this, we understood that a current carrying coil experiences a torque when placed in a magnetic field. This phenomena was used as principle for the working of galvanometer, which detects the presence of current in the electric circuit. Then we discussed the magnetic moment of revolving electron in greater detail. Also, we have the idea about how to convert galvanometer into ammeter and voltmeter. Try to solve some problems given in your physics textbook or exemplar problems related to the topic we discussed. You can share your solutions with your friends. Thank you.